Hey guys, welcome to the discussion video. This week we're going to be talking about perceptrons. So perceptrons are another machine learning model, in addition to naive Bayes that we can use to classify data. And the inspiration for perceptrons really come from the neuron in the brain. For a neuron, you have a lot of inputs, which are other neurons, and then these inputs go through some activation, and if they exceed the activation potential, then the neuron will fire, and otherwise the neuron won't fire. Right? So perceptrons are going to work in much the same way. For perceptrons, we have this set of inputs, which we'll call the features, which we're going to get from each data point. They'll go through some linear combination with some set of weights. And then in the binary case, if the result is greater than 0, then we'll output a +1 label. And if the result is less than 0, we'll output a -1 label. So mathematically, these formulations look like this. So in the binary case, we're going to take the dot product between the weights vector and the feature vector. And we're going to output the sign, whether it's plus or minus. In the multi-class case, each class will have some weight vector, w sub y for the class. And then our label for a given sample will be the argmax between the weight vector dot product with the feature vector. All right. So let's take a look at kind of visually how perceptrons are going to work. So here I've drawn kind of a set of data points that we can kind of imagine to be some set of data that we want to classify. What perceptron is going to be trying to do is finding a line that separates these two data points. So you can imagine that some line might look like this. So our goal is going to be to find the set of weights for the perceptron that will find this line. Okay? Now you can imagine for this example, maybe all of these feature vectors, since they're vectors, you can really think of them as arrows from the origin to where the point is, right? Like this. And then all of these negative sample points are also going to be arrows from the origin to where the point is. If you think back to your linear algebra days, the dot product is really just the projection of one vector onto the other, right? So if this is our separating line, the weight vector that's going to be associated with the separating line is going to be perpendicular and it's going to look like this. And then the dot product of this weight vector with any of these vectors is just going to be the projection of this weight vector onto the other vectors, right? So the dot product of the weight vector with maybe this guy here is going to be this, okay? And the dot product of the weight vector with these negative points will look like this. Okay, now once you draw it like this, it's kind of clear to see that the points that are kind of above this line or are less than 90 degrees away from this weight vector are going to have positive projections, and the points that are below this line are going to have negative projections if we say that this is our weight vector. Right, so our goal is going to be to find a weight vector that defines a separating line like this. All right, so let's get back to the slides. So when we're training our perceptron classifier, our goal is going to be primarily to find the weight vector that will correctly label the data. Right? So how do we do that? Well, this is going to be our basic algorithm. This is only in the binary case. We'll generalize to the multi-class case in the next slide. But for the binary case, you only have one weight vector. And initially, that weight vector is a vector of all zeros. And then we're going to loop through all the training data points until we can correctly label all of them. So the first step is to find the label that we classify for the training point x, which is just going to be the formula that you saw on the previous page, where we just take the sign of the weight vector dot product with the feature vector. Y star is going to be the true label of the training point. So if we predicted it correctly, then we won't change the weight vector. If we predicted it incorrectly, what we're going to do is we're going to update the weight vector based on the true label. So if the true label is -1, then we'll subtract the feature vector from the weight vector. If the true label is +1, then we'll add the feature vector to the weight vector. And we're going to continue this until all our training points are correctly labeled. So why does this work? Well, let's imagine for our example that our current weight vector looks something like this, which means that our separating plane is going to be the plane perpendicular to it, which is that. Now we're going through our training data and we come across a positive point right here. So this point is going to be below our separating line, which is going to mean that we're going to classify it as a negative point, so it's going to be classified incorrectly. So if this is the point, then the feature vector for this point is going to be this guy here. Now since we classified this point incorrectly, and the true label was +1, we're going to want to add this feature vector to our existing weight vector, like so. And now we'll have a new weight vector, which will be this guy. And this will give us a new separating plane here, which can now correctly classify this point. Okay, so if we have a positive point that we classify incorrectly, what we're going to do is we're going to push the weight vector towards that point. And if we push the weight vector close enough to that point, then we're eventually going to be able to classify it correctly. So that's the idea there. What if instead of a positive point, we had a negative point that we classified incorrectly? So let's go back to our original weight vector. Now say we have a negative point that occurs somewhere above the line. And so we end up classifying it incorrectly. So the vector for this positive point is this guy here. So what do we do when we have a negative point that we incorrectly classify? We're going to subtract this feature vector from our existing weight vector. So we're going to push the weight vector away from that point. That's going to give us a new weight vector and a new decision boundary, which is going to look like this. And as you can see, by moving the weight vector away from this negative point, we are now more likely to classify this point as negative. So that's kind of the idea behind adding a feature vector or subtracting a feature vector from our weight vector. Alright, back to the slides. So again, this is the training algorithm for the binary perceptron. Here is the training algorithm for the multi-class perceptron. And you'll notice that it's very similar, and there's only a couple of changes. So the first change is that in the multi-class case, there's a weight vector for each label y. So our initialization for the multi-class case is going to be to set all of these to 0. Also, the way to classify a point in the multi-class case is going to be to take the argmax over all labels of the dot product between the weight and the feature vector. And then the final change is if we classify it incorrectly, now we have two weight vectors to work with. So we're going to push the classified label away from the feature vector, and then we're going to push the true label that we didn't classify towards the true vector. Right, so what this is going to have the effect of doing is it's going to decrease the dot product between the incorrectly classified label and the sample, and it's going to increase the dot product between the true label and the sample. Right, so this has kind of a similar effect to what we just looked at for the binary case. So there are several problems that perceptrons can have, and I'm sure that many of you guys noticed this as we were talking about training and things. The first problem with perceptrons is that sometimes the data won't be separable. So what I mean by this is you can imagine that we have a set of training data that looks like this, where there's kind of no line that we can draw that will be able to linearly separate the two data sets, right? So during training, what we're going to see is we're going to first consider all the green points, and then our line will look something like this, and then we'll consider the red points, and then our line will look something like this, and then we'll just kind of go back and forth between these two lines as we do more and more training, as these 2 points here kind of fight back and forth. And this isn't ideal because in the training algorithm that we described, a situation like this would never end, right? We would kind of keep going and we would never be able to separate the data perfectly. So in practice, one thing that we can do to address this is instead of kind of training until we perfectly separate the training data. We can instead train until we kind of see this thrashing behavior, at which point we'll stop training and then we'll just kind of take the average, right? We'll average out all the weights of all the training iterations and we'll come up with something that looks like this, which is, it still doesn't separate the training data, but it's kind of a reasonable estimation for what we want. Okay, so that's one possible solution. Another case that you might see is maybe we'll have training points that look like this. So we have a bunch of pluses here in the middle. On the outside, we'll have these minuses. Okay, so again, this data isn't linearly separable, right? There's no line that we could draw through it to separate the data, but you can see that the data has some structure. So what we can do here is we can transform the data set from the original features F1 and F2 into a new set of features that will let us classify the data. Right? So namely, our new feature F3, we can write as maybe the distance from this point here. Right? So if you imagine that our only feature is the distance from this blue point, if we remap this into a 1D space where our one dimension is feature 3, where feature 3 is the distance from this blue dot, what we'll see is that all the green points are going to be very close because they have a low distance from the blue dot, and all the red points will be far away because they're farther from the blue dot. And now when we map the data like this, we get something that's linearly separable. So there's only a couple of different structures for something like this, but it's useful to look at past exams and be familiar with the different kinds of feature transformations that we will expect you to know. All right, so going back to the slides, the two solutions for inseparable data that we talked about is averaging the weight feature, and in some special cases, we can create a new set of features that will make the data linearly separable. All right, another problem that we might have is that the perceptron will not find the best solution. So again, consider that we have the same set of training data where we have some pluses here and we have some minuses here. Well, Perceptron is only looking for a line that can separate this data, right? So a line that looks like this is just as good as a line that looks like this, right? So what's the problem here? Well, line 1, you can see, will classify the training data just fine, but in a test scenario, you can easily imagine that we have some minus points that occur over here, or some plus points that occur here. All right? So the problem with line 1 is that it's not kind of robust to these small variations in the data. So we would much rather have something like line 2 to classify this data. Okay? And the way that we get line 2 instead of line 1 is by using SVMs, which stand for support vector machines, and Mira. So these are both going to be optimization problems, and SVMs are going to try to optimize this margin here. And so they're going to try to find the line that gives us the best margin of error. So SVMs and Mira, we don't really expect you to know super technically, like we don't expect you to be able to apply the minimization algorithm. It's definitely useful to know that these are out there and to know what they do. Okay, so back to the slides. The solution to this problem is using SVM or Mira, which will both try to optimize some metric that is going to give us the best line. Okay, so that just about wraps it up for this week. So good luck on your midterm, and see you guys in 2 weeks.